Hello everyone and welcome to Atensifelon Lectures. Atensifelon is a research company that employs expertise in neuroscience and computer science with the intent to use a regular computer program to control the brain of a living animal. Atensifelon has advanced research in this field, and this series of lectures illuminate our belief in this possibility. This is the second in the series of lectures where we begin from what is common knowledge. A link to the first lecture is on this video. In this second lecture, we shall be looking at how a neuron expresses and/or logic. How a neuron expresses and/or logic. So, first of all, if you remember in the last video, the first video we did, we said that a neuron and logic gates are very similar. So in a logic gate, low voltage is a 0, while high voltage is a 1. In a neuron, when the neuron is not firing, that's a 0. When the neuron is firing from its axon, that is a 1. So here, we've put a picture of what that neuron looks like, and these are the logic gates. So these are logic gates and or, exclusive or nor, and then we have our neuron. So a neuron expresses the logic that a logic gate expresses. So in this lecture, we shall take a look at a video that talks about graded potential. So the thing is, how do neurons communicate? How does a neuron know whether to fire an action potential or not? So that's what we want to look at in this video. How does a neuron know how to fire action potential? So I'm going to play a video. This video is on YouTube by Dr. Mike. You can visit his website and then look at some of the cool videos he has made there too. So here he's going to talk about graded potential. Just listen to the video.
Hi everyone, Dr. Mike here. In this video, we're going to talk about how a neuron can be stimulated to send a signal or be told not to send a signal. Now very quickly, what you need to remember is in order for a neuron to send a signal, so think about it, you've got a neuron with its big long axon. Remember that excitable tissues or cells, like neurons, have a charge difference from inside to outside. It's more negative inside than it is outside. In actual fact, if you were to compare that charge difference, it's negative 70 millivolts different. So inside is negative 70 millivolts compared to outside. So it's sitting right here. This is what's happening when the neuron is not firing off and it's resting. That's called the resting membrane potential. Now, when we want this neuron to fire off and send a signal, what we do is we need to open up channels that let positive things like sodium and calcium inside to change that negative to a positive. So it needs to move up to a more positive area. Now, once enough positive ions have moved in, enough positive sodium or enough positive calcium have moved in, and it shifts this graph up, once it's positive enough that it's negative 55, so it goes from negative 70 to negative 55, this is what we call the threshold. Once it hits negative 55, all of these positive channels open up. All of these positive sodium channels just go boom, 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 and they open up in this domino-like fashion, letting all this positive sodium move in. It starts here, it moves in, and then it goes dunk, 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 all the way down that axon. That's actually what an electrical signal is. That's how we know that something's touching my finger. Sodium ions are simply jumping into neurons all the way down my arm, into my spine, up to my brain, okay? But what stimulates these sodium channels to open up in the first place? This is that graded potential. So what I've got here is a neuron, and it's receiving a signal from two different neurons. It's got a neuron here that's sending a signal that's excitatory, and this neuron here is sending a signal that's inhibitory. Remember, neurons don't actually touch one another. There's a space in between that we call the synaptic cleft, and something needs to cross that synaptic cleft. That something is a neurotransmitter, which is simply just a chemical. For the excitatory neuron, the neurotransmitter it sends is an excitatory neurotransmitter. In this case, glutamate is the excitatory neurotransmitter that I chose. And for this one, that's inhibiting this neuron from sending a signal, it's releasing an inhibitory neurotransmitter. In this case, I've chosen GABA. Let's first start with the excitatory. So this neuron releases its neurotransmitter glutamate into the synaptic cleft. Now, it diffuses across from its area of high concentration to its area of low and needs to bind to specific glutamate receptors. Now, what I've drawn up here are two different types of glutamate receptor. This glutamate receptor that it's bound to is sodium specific, which means when the receptor binds to this channel, when the neurotransmitter binds to this receptor, it opens up its lid, and positive sodium, which we know sits predominantly outside the cell, wants to diffuse down its concentration gradient and go inside. So positive sodium goes from outside inside once the excitatory neurotransmitter has bound to it. That means as the positive sodium goes in, it takes its positive charge with it, and it starts to get a little bit more positive inside the cell. Now, this same thing happens if the excitatory glutamate neurotransmitter binds to another type of glutamate receptor called a calcium receptor, which flips its lid open and positive calcium comes in as well. If positive calcium comes in, it becomes a little bit more positive inside and again starts to move closer and closer to this threshold of -55. If enough positive sodium come in, or enough positive calcium come in, or enough positive sodium and calcium come in, that it hits -55, then all these sodium channels open up and the signal is sent. Okay? Now this is where we start to make graded potentials. If only a few sodium channels open up, then this only starts to get a little bit positive. And if that's it, it drops back down to its normal -70. If a couple of positive sodium opened up here, and then a couple of positive sodium open up here and here and here and here at the same time, then you add up all the positive charges that they're letting in one go, and it'll hit the -55. That's what we call spatial summation. Spatial summation is where multiple channels at the same time across different areas open up, let all this positive sodium in, and it's enough to hit -55 and send an action potential, which is that signal that's sent. Now that's spatial summation. There's another one called temporal summation, which means over time. So that means if we just focus on the one channel and we open up that sodium channel, positive sodium goes in, then it closes, it goes up like this, and then may stop a little bit, and then we open it up again, it may go like this, close it, open it up again, goes like this, and then finally over time, enough positive sodium enters the cell that it hits the threshold and a signal sent. So that's temporal summation, spatial summation. Now the other thing is that because it's letting positive things in, it's an excitatory signal. Here for GABA, what it does is it binds to a GABA receptor that's, when it opens its lid, negative chloride comes into the cell. Now because it's negative, it carries its negative charge with it and makes it even more negative inside the cell, which makes it harder to send a signal. And that's an inhibitory signal. So excitatory signals make it easier or more positive inside to send a signal, and inhibitory signals make it more negative inside or more difficult to send a signal. This is what we call the graded potential.
Thank you so much, Dr. Mike. I hope you enjoyed that video. So we'll move on with our lecture. All right. So according to Dr. Mike, he has told you there that graded potentials are formed when axons, nearby axons that are connecting to a neuron release neurotransmitters to that neuron, and then by doing that, they raise the membrane potential of that neuron. So one thing we must highlight is that every neuron has a location called an axon hillock. That is where the action potentials begin. So if the membrane potential as measured at the axon neuron goes from -70 millivolts to -55 millivolts, then an action potential is initiated from the axon hillock that travels all the way down the axon. So here I've shown a picture of our regular axon. Thank you very much, John Hopkins Medicals. So this is our regular axon. So I've just shown a caricature of that axon here because I want to illustrate something. So this round shape here, we shall assume that to be the cell bodies, and then the holes that you see here are what we call ligand-gated ion channels. These are the ion channels, like the sodium ion channels, the calcium ion channels, or the chloride ion channels that we have connected to the body of this soma. And that connection could be through the dendrites or directly on the soma. So just take it that I'm trying to illustrate something to you here, that these little dots, black dots you see here, are actually ligand-gated ion channels that open up and allow sodium to come in, calcium to come in, or chloride to come in if we are looking at inhibitory neurons. Okay. All right. So we want to do some illustration here. I have here a graph where I'm going to plot membrane potential as against what is happening in the axon, in the neuron, right? So let's have an example. You see here we have a red. That means one ion channel, ligand-gated ion channel has opened and sodium has come in. So when sodium comes in, there is a limited amount of sodium that can go in through this place before that channel closes. So if it is just one channel that opens, you have a small graded potential that will eventually die off. What makes it to die off? We have things like the sodium-potassium pump. We have leaky channels of leaky channels that will allow it to restore its state back to the negative 70 millivolts. So if this is all that opens and sodium goes in and then it closes again, then what you're going to have is just a bump. The graded potential as just a bump that dies off, and the membrane potential as measured at the axon hillock returns back to negative 70. So for the purpose of this illustration, let's assume that the opening of every ligand-gated ion channels introduces 1 millivolt, brings in 1 millivolt inside the cell. So we are saying the opening of this ligand-gated ion channel introduces 1 millivolt inside this cell. So which means if I go ahead and open 2, then it will become 2 millivolts. 2 millivolts. So we have negative, this negative 69, negative 68. So it will take you to 2 millivolts and then it will eventually die out. Those two ligand-gated ion channels will eventually close, and then the membrane potential will return. Remember, we need to go from negative 70 to negative 55 before an action potential can trigger. So if I ask you, how many ligand-gated ion channels can open before, excuse me, how many ligand-gated ion channels can open before we get to this threshold? If each ligand-gated ion channel introduces 1 millivolt. So if you see 1, 2, 3, before you get to negative 55, you are talking of 15 ligand-gated ion channels. Let's see what happens when we open 10 of those ligand-gated ion channels. So 10 of those ion channels open, and then sodium or calcium flows in. The membrane potential as measured at the axon hillock will rise, and when it gets to negative 60, that's after 10 millivolts, then it begins to die out. Why is it dying out? Because the sodium potassium pump and other mechanisms of the cell, leaky channels, will restore the membrane potential back to minus negative 70. All right. So what now happens when I take it up to negative by 14? I open 14 channels. Again, it will rise, the membrane potential will rise. It will not get to this negative 55, and once it doesn't get there, it dies out gradually. So what happens when I take it to 15, when I open the 15th channel? So now we have 15 ligand-gated ion channels open. Remember, we made assumption at the beginning that each ligand-gated ion channel introduces 1 millivolt to the membrane potential as measured at the axon halo. So if I open 15 ligand-gated ion channels as an example, then this will take it to the threshold. The threshold is negative 55. So from negative 70 to negative 55, that's 15. It takes it to that threshold, and once it gets to that threshold, the axon helix will sense that the membrane potential has gotten to the threshold, and then it will fire an action potential, and that's why you see that this goes up. Then the membrane potential begins to rise astronomically, fires an action potential, and eventually it's restored back to negative 70. So an action potential will flow from this axon helix all the way on the axon down to the axon terminal. All right. So now that we understand this, what if I have two neurons, neuron A and neuron B, that are connected to neuron Z? So neuron A fires an action potential and releases neurotransmitters. Could be acetylcholine or any of the neurotransmitters that is excitatory. Release it into the synaptic cleft. It binds with the dendrites of this postsynaptic neuron, and then it opens those ion channels, and you have sodium from the environment flowing into the cell, raising the membrane potential of this neuron Z here to say 2 or 3 or 7 millivolts. Now, if you have two neurons that are doing the same thing, we want to analyze this and see what interesting situation we can have. So two neurons, A and B, are releasing neurotransmitters to a third neuron, neuron Z, and we want to see what effect these two neurons would have on this neuron and see if there will be an action potential. So again, let's say, going back to our picture, if we have a neuron A, right, releasing neurotransmitters to neuron Z such that you have, say, 8 of such ligand-gated ion channels as indicated here, 8 of them open, and at the same time, or about the same time, neuron B also releases neurotransmitter to neuron Z, opening up, say, 7 ligand-gated ion channels here, which may be sodium channels. So what will happen? You are now having 7 sodium channels open here by neuron B and 8 sodium channels open here by neuron A, bringing the total to 15 ligand-gated ion channels that are open. Remember, we said once it gets to 15, assuming that each of those ligand-gated ion channels introduce 1 millivolt, when we get to 15, the axon helix will sense that the threshold has been reached, and then it will fire an action potential. So in this situation, when axon A, when neuron A opens these channels and neuron B opens these other channels, bringing the total channels open to 15, thereby raising the membrane potential as measured at the axon helix up to negative 55 millivolts, there will be an action potential. So it means for us to have an action potential, you need neuron A and neuron B to fire simultaneously. So when we are summing up this, the action of neuron A and neuron B about the same time, we call this spatial summation. Spatial summation. So for this series of lectures, we shall specifically be looking at spatial summation. At other lectures, we shall look at temporal summation. So there is a spatial summation of the effect of neuron A and B on neuron Z causing an action potential. So if you look at this, we now have a truth table. I'm going to show you with a truth table. So here where you have A means neuron A. When A is 0, it means neuron A is not firing. It's not bringing in any, it's not firing any action potential, thereby not opening any ligand-gated ion channels. So when A is not firing and B is not firing, that means A and B, nothing is happening here, then Z, which is A dot B, is 0. That means neuron Z will also not fire. The 0 here means neuron Z will not fire an action potential. Okay, now let's look at another situation. When A is not firing, which means neuron A is not bringing in any neurotransmitters as to open these ligand-gated ion channels, it's not firing, and neuron B is firing, where we have B is 1, so B fires and opens its respective ligand-gated ion channels. Then we only have 1, 2, 3, 4, 5, 6, 7 ion channels open, which is not sufficient to raise the membrane potential as measured by the axon haloc to -55 to bring out an action potential. So if we look at this, that's why we have 0 here, which means A is not firing, B fires. The two of them happening simultaneously will not bring about an action potential, which is 0. Now let's look at the other case, the third case. If A fires, opens up its 8 ligand-gated ion channels, but B does not fire, so which means these channels are not open, then we have a total of 8 channels that are open. 8 channels opening will bring the membrane potential 8 millivolts up, going by our assumption that one of them opens 1 millivolt. It brings it 8 millivolts up. By that, it is not sufficient to trigger an action potential from the axon halox. So again, when A is 1, firing, and B is 0, not firing, then there is no action potential from Z. That's why we have Z. Now look at this, the last situation, where A fires and B fires simultaneously. A and B fire simultaneously. What happens? A opens its 8 ligand-gated ion channels. B opens its 7 ligand-gated ion channels. When you total the two of them together, you are going to have 15 ligand-gated ion channels open, which will bring the membrane potential from the resting state of -70 millivolts up to -55 millivolts. And once the axon halox senses -55 millivolts, the axon halox will fire an action potential. So that's why you see that in this truth table that I've created, when A is 1, which means A is firing, and B is 1, B is firing, then Z or Z will fire. That's why you see Z here is 1. What I've just illustrated to you is what we call an AND gate. And you can see in electrical circuit, this is what is called an AND gate. So for you to have an output from the AND gate, then A has to be 1, which means A is firing, and B has to be 1. So A is 1, B is 1. That is the only time there will be an output from the AND gate. So this neuron Z is acting like an AND gate, where when two inputs A and B fire simultaneously, remember we said we are going to be looking at spatial summation. At a later video, we shall consider temporal summation. For now, let's concentrate on spatial summation. When the two of them fire simultaneously, then neuron Z will fire an action potential as shown in this truth table. This is what we call an AND gate, a neuron acting as an AND gate. Let's look at another scenario. Suppose neuron A was not actually connected to 7 or 8 ligand-gated ion channels, but rather it was connected to 15 ligand-gated ion channels, right? So when A fires, all 15 ligand-gated ion channels will open up, allowing sodium or calcium to flow in. Same thing with B. B is not connected to 7 ligand-gated ion channels, but connected to 15 ligand-gated ion channels. So anytime B fires, then all the 15 ligand-gated ion channels located here will open up, allowing sodium to flow in. So let's see what happens in this neuron. So looking at this truth table, when A does not fire, which means A is not firing an action potential, thereby not opening any of the ligand-gated ion channels, then nothing happens at the corner of A. When B also is not firing, like you have AB, A is 0, B is 0, B is also not firing, then nothing is happening at the section of B. So which means no ligand-gated ion channel is open. So the membrane potential remains at negative 70 millivolts, and so there will be no action potential. So we see AB, A not firing, B not firing, then Z, which is a sum, which is the product of A and B, is 0. So Z or Z will not fire. That's why we have 0 here. Now let's look at the second scenario. If B fires, B opens, fires, and A does not fire. So A is not firing, so nothing is happening at A. But B fires an action potential, opening 15 ligand-gated ion channels. This will cause calcium or sodium ions to rush into the cell, raising the membrane potential, going by assumption that one ligand-gated ion channel raises the membrane potential by 1 millivolt. This will cause 15 millivolts, the membrane potential to rise by 15 millivolts, taking the membrane potential from negative 70 millivolts up to negative 55 millivolts. That will trigger an action potential. So at this axon helix of neuron Z, an action potential will be triggered, and then you have a firing of action potential because 15 ligand-gated ion channels were open here due to B firing. So that's why we see 0, 1 leads to 1. Let's look at a situation where A is 1 and B is 0. So if A fires, opening 15 ligand-gated ion channels, but B does not fire at all, we still have sufficient ligand-gated ion channels open, bringing the membrane potential to negative 55 millivolts, causing neuron Z to fire an action potential from its axon helix. So if we look at this third situation, A is 1, B is 0, 1 would mean that Z will fire. Z will fire because A is connected to 15 and B is connected to 15. So either of them that is triggered will cause an action potential to be fired. What if we have the two of them triggering? Well, then you have more than enough action potential. In fact, you have 15 millivolts caused by A firing and another 15 millivolts caused by B firing, bringing it to a total of 30 millivolts increase in the membrane potential of neuron Z. So that is more than enough. That is way above the threshold, causing the axon helix to fire an action potential. Remember, the action potential will either fire or not fire. It has nothing to do with whether it is 30 millivolts increase or 15 or 25 millivolts increase. Once the threshold of negative 55 is reached, an action potential will fire. So the two of them, A and B firing, will lead to an action potential firing from neuron Z. If you look at this, you see this is an OR gate, which means whether A or B fires, the neuron Z will fire. So in digital computer logic circuit, we use this symbol to represent an OR gate. If A fires, then this gate will fire an output. If B fires, this gate fires an output. The only time this gate will not fire is if neither A nor B is bringing it a 1 to this logic gate, then it will not bring out some. It will not fire any output. So it's the same thing in this neuron. If A and B do not fire, then this neuron will not fire. But if either A or B or both of them fires, then this neuron will fire. So this is a neuron, a two-input neuron, A and B, exhibiting an OR operation, an OR logic. Okay, so this is another one where you have a 3 input, A, B, and then we have a C. Each of them 15, 15, 15. So this is a 3-input OR gate in which if A fires, the neuron fires. Or if B fires, the neuron fires. Or if C fires, the neuron fires. Or any combination of the 3 that fires will cause this neuron to fire. The only time this neuron will not fire is if neither of these neurons, A, B, or C, are firing. All right. So this brings us to the end of our lectures today. Thank you very much for listening.